Alright, hey, wanted to do a seventh and probably final video of this series about real numbers. And I wanted to begin by talking about where this whole sort of line of questioning about packing numbers into numbers and so on came from. And for me, it actually started a few years back with a dream I had. Basically, in this dream, I was some kind of secret agent. I was sent into a party to steal something. And I got in, I made conversation, I snuck away, I cracked a safe, I grabbed this object, and I left. And the thing that I was stealing was a piece of plastic, about that size, clear plastic like lucite or something, and it had embedded into it three metal bolts sticking out. And after I left the party in my dream, I woke up and I was laying in bed thinking about well, that's a weird dream, and I was wondering what would be the significance of this object. So I started making up stories, and usually spy dream, you're stealing something, you're stealing information, right? Is a pretty likely scenario. So I started wondering what could be the information stored in this piece of lucite with three bolts in it. And it could have something to do with the orientation of the bolts, where they are relative to each other, and so on. And I started to think about distance. And if you assume that one of these is sort of a base marker, we could take the distance to the furthest bolt and call that a distance of 1. And then the distance from the base to the third bolt, we would call that x. And in this way, we could have a self-contained system that lets us store a real number, x. And we don't need to rely on the accuracy of some external meter stick or something. It's completely self-contained. This tells us what a unit length is, and then if this is 2/5 of that, then this represents the number 2/5, 0.4. So I was thinking, okay, so maybe this is a weird way that somebody was storing a real number. What would be the significance of a real number? Well, it could be, a coded password or an account number or something like that. But then I thought, what if you wanted to store like the position of something on planet Earth? Maybe you want to store a latitude and a longitude. And how would you do that in a single number? Because we don't want to start putting in multiple bolts here. And so, maybe our latitude we represent as an 8-digit number, 4 digits before and 4 digits after. And our longitude, maybe we store, well, we don't really need 4 digits in front, but one could be a plus or minus sign maybe. But, have some fixed point coding like this. And then we take these 16 digits and we put them together into a single real number between 0 and 1. So it's like, yeah, okay, we could store latitude, longitude. That's kind of cool. By the same token, you could store multiple pieces of information, right? We could store latitude and longitude and a timestamp and a date and all kinds of things like that by, continuing this. And so I started, just kind of kicking around ideas for how much information and what ways could you store information in a single real number between 0 and 1. Alright, so, and we saw in some of the earlier videos, we could take multiple pieces of information, we can interleave them, we can increase the number of digits as we make multiple passes over these numbers to store more and more precision of a set of values, and so on. So along those lines, suppose you wanted to store, say, the temperature at different points along a line. So, take some interval, and we want to store the temperature here and here. Well, that's just two numbers, right? But maybe we want to store it at 5 points along this line. Well, that's 5 numbers, and we've seen ways to do this, right? We could store it at the beginning and the end, and then we could store it at the beginning, the middle, and the end, and then at the beginning and by distances of a quarter out to the end, and we can keep interleaving where we take our readings. And so we can store temperature readings in this case, you know, at different points down to kind of whatever precision we want. And so more generally, we could think of this as like, you know, storing some function, y equals f of x. And at each point x, we want to know what the value of this function is, whether it's temperature or, you know, humidity or something else. And so that's one possibility, right? So let me at this point make a side trip here into this idea that I'm working along a line, but you know, if you actually wanted to store information about different points in a two-dimensional region, we can do the same thing, right? We just have to break our region up into a set of points, and we can, you know, enumerate our way through these in some prescribed order. And you know, if it's a finite set of divisions, it's a finite and therefore countable collection of points, and we can just order them. And so, you know, instead of having a line, we can basically take that line and wiggle it through a two-dimensional space. And we can do the same thing with a three-dimensional space, because we can use this approach to store information at this top level, and then we can move down a little bit and store information on this next layer, and then move down a little bit and store information on this next layer, and so on. So everything that I'm talking about we can do in a three-dimensional volume, as well as a two-dimensional area or a one-dimensional line. But I'm going to stick to a line just because it's a little easier to talk about some of these concepts, and it's easier for me to draw. But you know, extend it to three-dimensional volume in your head. All right, so here's the idea. So you know, I was thinking like, well, what would be the ultimate information to store in this weird little, you know, information storage system? How about the state of the universe, right? So imagine that we're going to go through you know, some region of space, and we're going to store, I don't know, you know, this is not scientific. We're going to store temperature. We're going to store information about whether there's a particle at that location, and if there is, what type of particle, a quark, a muon, an electron, whatever. Maybe what's its velocity, what's its acceleration, what is its spin or its color or other quantum properties, right? I'm obviously not a physicist, but you know, we could go through our region, or you know, go along our line, and at each of these points store you know, multiple functions. So here's our temperature curve, and here's our velocity curve, and so on. And we can, you know, store these different values just like we store latitude, longitude. So a couple of ways to expand this out. One is the scale. The second is the accuracy of location, which I'll think of as x, and the accuracy of the value, which I'll think of as f of x. Okay, so what do I mean here? If we have a fixed interval, you know, from 0 to 1, we can, you know, go through here and store values at the endpoints. We can store values at the middle. We can come back and go by quarters. We can come back and go by eighths, and so on. See the previous videos. But what if instead of going from 0 to 1, we want to go from 0 to 2, or from -2 to 2? Or what if we don't want to bound this? What if we don't believe the universe is bound, and we want to be able to store this for arbitrarily large absolute values? So that's one question, is how do we do this across, you know, an arbitrarily large scale? The second question is, you know, maybe we're dividing this into 10 regions, and so we have 0, 0.1, 0.2, 0.3, but maybe we want to know the value at 0.15 in between these 2 points where we're storing, you know, the value of our function. How close can we get to this? Well, you know, if we keep dividing, we can get down very, very close to any rational number and eventually hit it exactly. But for an irrational number, like pi minus 3, any of these subdividing schemes where we keep moving over by smaller and smaller increments is not going to get us to this irrational number, but it will get us arbitrarily close. So how close can we get to x? And then the other question is, how close can we get to the function value at that point x? Because if the function value needs an infinite number of digits to be represented, we can't store an infinite number of digits because we'd never get to the next value in our string of digits. But it turns out we actually can store with arbitrary precision the function value. So we've seen this in previous videos. Let me just spell it out for you again here. So here's what we're going to do. We're going to store values at x equals -1, 0, and +1. And at each of these, we're going to store a single digit of the function value. So we're going to assume our function is between 0 and 1. So we're going to store a single digit of the function value. All right, so our magic number that we're going to create is going to have a first digit, which is f of -1, digit 1. And then we're going to have f of 0, digit 1, and then f of 1, digit 1. And then we're going to go through the values -10, -9.9, -9.8. all the way up to +10. So we're going to bump up the scale by 10x. We're going to bump down our increment by 10x. And we're going to store 10 digits of, or let's just say 2 digits of each function value. So after this, we're going to store f of -10, and we'll store the first 2 digits, and then f of -9.9, and we'll store the first 2 digits. F of -9.8, we'll store the first 2 digits, all the way up to f of 10, 2 digits. And then we're going to make a third segment of digits in our magic number. We'll call this magic number m for magic. And here we're going to go from -100 to -99.99, -99.98, all the way up to 100. And so the next number we store will be f of -100, and we'll store 3 digits, and then f of -99.99, and we'll store 3 digits, and so on. All right, so you get the idea. What does this mean? This means that, if we want to know the function value at something around, 1,000,000, we can just go far enough out in here that we're looking at the section corresponding to, probably our 7th segment of values, which will go from, -1,000,000 up to a +1,000,000. So 7th or 8th, if we want to get something between 1,000,000 and 10,000,000. And at that point in our magic number m, we will see all the digits, the first 8 digits for, f of -1,000,000, f of -1,000,000, plus 1,000,000th, plus 2,000,000ths, plus 3,000,000ths, and so on. So we can get to a point in our decimal expansion for m where we're looking at things with the right scale. And, if we're looking at a scale of around 1,000,000, our increment as we move from one tick mark to the next is 1,000,000th. And if that's enough accuracy of our location, we're fine. If we want greater accuracy, if we want accuracy of, say, 1,000,000th, we would go out 3 more segments. We'd be moving from -1,000,000,000 to 1,000,000,000, but our increment would be 1,000,000,000th. And, if we want to get to some precise value of x with, a digit in the 9th decimal place, we'll get there eventually, because the numbers that we're storing in this magic number m represent the decimal expansions for f of x as x moves by 1,000,000,000th from -1,000,000,000 to 1,000,000,000. And finally, depending on how many decimal points we want in the value of f of x, Well, if we're in the billionth region, we're going to have 9 decimal points. If we wanted 12 decimal points, we go out to the 12th or 13th segment, where we're going from negative a trillion to a trillion. We wait till we get to the number that we want, stepping over by 1/trillionths, and then at that point we find, 12 digits corresponding to the value of f of x at that value of x. So packed inside this one real number, we've got an unlimited scale, the ability to get arbitrarily close to any number x, and to eventually get exactly to any rational number x, and the ability to pull out as many decimal places as we want from the value of f of x. And then, of course, if we're packing in, several pieces of information, we can just, do this for f, and then do it for g, and then do it for h, and then do these for f, g, and h, and then do these for f, g, and h, and so on. So we can interleave different types. And again, we don't have to go along a line. We can take that line and wrap it into something pseudo space filling to cover an area or a volume. So we can store this information inside this one real number. So the thing that gets more interesting, and that pulls in this question of are real numbers real, is if we imagine trying to actually do this, ignoring the fact that it's obviously not practical. But suppose we had this block, and we've got some way to measure precisely, so we can't just use a ruler, but we've got to maybe say, okay, we're going to go to the center of these bolts. They have to be perfect circles or squares or something, so we can find the center, or they have to be infinitesimally thin, which is harder. And we can assume there's some way to measure that and some way to measure this and see what fraction of that distance it is to get our number x. What happens if we try to do this to actually code information about the universe? And there's a few things. So the first thing is, suppose that space-time is continuous. Suppose that space does not jump discretely, that time does not jump from one moment to the next, but that it flows continuously. It raises the question of, there are an infinite number of points between here and here, an infinite number of x's at which we might want to know the value of f. And we can get closer and closer and closer to any of those, but there are some points we will never get to exactly. For example, pi minus 3, right? Because there's no, in this scheme, there's no tiny little fraction that if we start from some integer and count up will get us exactly to this, right? It's not a rational number. We can't write it as a fraction. So if the universe is continuous, if space is continuous, then there will be points we won't be able to get to, okay, which may be a problem, or it may not, because experience tells us that things tend to change smoothly. In other words, suppose we want to know the temperature at this point, pi minus 3. So this is going to be our x, and we've got some, f of x. Okay, if things are smooth, if things are not chaotic, the closer we get within reason, right, the closer we get to x, the closer f gets to f of x. Okay, that's a non-chaotic system. Far away, sure, if we're over here, we might, get further away. But at some point, if we get close enough, we will find that, the closer we get to this value of x, the closer f gets to the value of f of x. Okay, that's a non-chaotic system. If things are not chaotic, then, depending on how close we want to know the value of f of x, we don't have to get exactly to x. We can get, within, I don't want to say epsilon delta, but, get within some delta and know that f is within some epsilon. But that's for a non-chaotic system. That's for a continuous function. Assuming that that's how things work, things don't suddenly jump and change value, well, that means that, this value of x will store all the information we need to get a pretty good approximation of the state of everything at all times. But there's the problem of how do we actually position this? All right, so the problem here is if things are non-chaotic, if things change smoothly, how do we position these bolts? Because the idea of being able to specify a precise precision for this bolt would mean if we looked, along some line at different points and we were looking at maybe a binary value to say, is there a particle present? We would see zeros at all of these. And then here we would see ones saying there's a particle, and then maybe here we'd see zeros again. But to be able to precisely locate this, there has to be some cutoff point where everything over here is 0, there's no bolt present, and everything over here is 1. There is a bolt present, until we get to some other cutoff, and then we get back to zeros. And this notion of, if we were to draw a function saying, is there, a particle present at this location, it would be a step function, right? And nature doesn't like step functions. This is why CDs sound the way they do as opposed to vinyl, because, transistors approximate steps better than vacuum tubes. Different topic. But nature does not like step functions. Things don't generally change instantaneously, so particularly if we're assuming that things change smoothly, then perhaps in some way this position, is there a particle present at a location, takes on a continuous range of values between 0 and 1, so that in fact, maybe in here we see something like, 0, 0.1, 0.3, 0.75, 0.9, and then it comes to a 1 over here. And how do you locate something when you have this kind of, sort of blurring of the edges? And this, of course, smacks of Heisenberg or Schrodinger's probability function for the position of an electron and so on. So in scenario 1, where space-time is continuous but things change smoothly, that lets us store all the information we want in this single real number, but we can't actually code that using this 3-bolt system, because the idea of trying to store an infinitely precise real number based on the position of these things sort of breaks down. The second possibility is that things don't always have to be continuous. We can have chaos. We can have a step function. We can have a situation where up to here, we have one value for our function, and then at that point it suddenly takes on a different value. Well, that's chaos, right? That's a situation where, our function looks like this, and sometimes as we get closer to a value x, our function gets closer to f of x. But sometimes, if this is our value f of x at this point, as we get closer and closer and closer to that point, we're not getting closer to f of x. And if that's the case, right, we could have, a very precisely located center location for these 2 bolts that would code an exact value for x, but we can't use that coded information to know the value at something like, an irrational x location, because it's possible at that point our function jumps, or maybe it's one of these horrible continuous nowhere functions, something like Brownian motion, almost, where being able to tell the value very close to this tells us nothing about the value actually at this point. So again, our scheme is foiled. The third possibility is that space and time are discretized, and so there is a minimum length, a Planck's constant, 10 to the minus 36, something like that, meaning that once we divide our interval down into these tiny little steps that correspond to the smallest distance that represents an actual point in space, we can get to exactly every location in our coded space and read out the value of f with arbitrary precision. So now we have a perfect representation of what's going on at every point in the universe at all points in time. But the problem there is, if space is quantized, if it's discretized, we cannot place this bolt anywhere that we want. We can only place it within whatever our quanta is, our Planck's distance or whatever, and so we can only approximate this magic number that codes the universe. And so again, our attempt to code the universe is foiled by this scheme. All of these problems are also exacerbated, when we try to actually code information about this system itself as part of the universe, because if this needs an infinitely precise, possibly irrational distance, from some base point, and we want to be able to store it, as a impulse function, which tells us exactly where the particle, corresponding to the center of this bolt first appears. That works against all the features of the universe that would make it possible to do this coding in the first place. So all of this, sort of goes back to this original vague question of, are real numbers real? And it feels like, if we really want to think about describing any of these things, maybe we need a very, very large fixed point number. And maybe that's closer to what we can use to actually describe these scenarios, as opposed to an arbitrary real number that could code, in more or less unlimited set of information. Anyway, that's just some stuff I've been kicking around. All right, thanks.